Ever wondered how your email, your video stream, or that latest game update finds its way through the labyrinthine pathways of the internet, often arriving in milliseconds? It's not magic, but it is a profoundly intelligent system built on meticulously designed routing protocols. Today, we're taking a deep dive into one of the most foundational and, well, powerful of these for modern networks, OSPFv3. This isn't just about understanding acronyms. It's about peeling back the layers to see the unseen architecture that guarantees our digital world keeps moving. We've gathered a stack of detailed sources, from configuration guides to architectural deep dives, ready to unpack its essentials.
Yeah, and what's truly fascinating about OSPFv3, I think, is that it acts as this highly efficient real-time GPS for data within large-scale IPv6 networks. It's constantly calculating the fastest, most optimal routes.
A GPS for data. I like that.
Exactly. And if we connect this to the bigger picture, OSPFv3 isn't merely an update. It really represents a fundamental architectural evolution from its IPv4 predecessor, OSPFv2. It's purpose-built, to navigate the vast expanded address space and meet the evolving demands for scale and resilience in today's and tomorrow's digital infrastructure.
Okay, so our mission today is to demystify OSPFv3. We'll explore what makes it tick, the intricate design choices behind it, and why it's so pivotal for modern network infrastructure. By the end of this deep dive, you'll have a clear, well-informed understanding of this critical protocol, quickly and thoroughly. All right, let's dive right in then. When we talk about OSPFv3, we're dealing with something fundamental, a link state protocol. For those perhaps familiar with older routing methods, or even just as a refresher, what exactly does link state signify in the practical operation of a network? And how does OSPFv3 specifically embody this?
Right. So at its core, OSPFv3 is an interior gateway protocol, an IGP, designed specifically for IPv6. That immediately positions it for routing within a single administrative domain, distinguishing it from, say, exterior gateway protocols like BGP that handle routing between different domains.
Okay, so internal routing.
Exactly. And the link state aspect is indeed the star here. It means that every single OSPF device in an area acts like a meticulous cartographer. Each device originates link state advertisements, LSAs we call them, which are essentially digital postcards. They contain precise, up-to-date info about itself and its directly connected links, their status, their cost, what neighbors are reachable, that sort of thing.
Digital postcards, okay.
Yeah, and these LSAs aren't just sent to one place, they're reliably flooded throughout the entire OSPF area. Once every device receives a complete synchronized collection of these LSAs from all the other devices, they all independently run the shortest path first, or SPF algorithm.
SPF.
Think of this algorithm, often based on Dijkstra's, as their sophisticated GPS calculator. It takes all those map pieces, assigns a cost to each link, like maybe based on bandwidth or delay, and then meticulously computes the most efficient, lowest cost, loop-free path from itself to every other destination in that area. The beauty here is that every router achieves a consistent, comprehensive topology map. This leads to really rapid convergence when network changes happen.
So the sheer ingenuity, then, of the link state approach is that every router gets this complete, consistent view of the network topology. What are some of the most profound benefits this offers compared to, say, a distance vector protocol, which only really knows about its immediate neighbors?
Well, the primary benefit is really speed to convergence and a loop-free environment, because every router has that complete map. When a link goes down, they can instantly recalculate the entire network's shortest paths. They don't need to wait for information to propagate hop by hop like you see in distance vector protocols. This makes the network incredibly stable and responsive.
Faster and more stable. Makes sense.
And a crucial differentiator for OSPFv3 itself is that it natively supports IPv6 addresses and prefixes, unlike OSPFv2, which is strictly for IPv4. But native isn't just a simple address swap. It reflects a fundamental architectural shift. For instance, while you configure OSPFv3 on an interface, meaning you enable it for that specific port, the protocol itself actually operates and exchanges information on a per-link basis.
Per link, not per interface. How does that work?
Yeah, it's a subtle but important distinction. OSPFv3 primarily uses IPv6 link local addresses for neighbor discovery and forming adjacencies. This kind of detaches the OSPF process itself from the globally routable IP address configured on the interface. It allows for a cleaner separation of concerns and, arguably a more robust design, even though it does introduce some new considerations for network admins.
That distinction, operating per link via
Yeah.
link local addresses,
Yeah.
that really highlights the IPv6 native design thinking.
Yeah.
Now, to get this sophisticated network GPS running, you obviously have to configure it. What are the essential first steps an administrator would take? Like the absolute basics to get OSPFv3 up on a device.
Absolutely. The very first thing every OSPF device needs for stable operation is a unique identifier. We call it the router ID. This is typically a 32-bit value, often formatted like an IPv4 address, even in IPv6 networks.
Oh.
It's set using a command like iprouter_aid. This ID is used throughout the OSPF domain to identify the router regardless of the IPv6 addresses on its interfaces.
Okay, router ID first. What next?
Well, before you can even enable OSPFv3, you have to make sure the device is actually ready for IPv6 traffic. This usually means enabling IPv6 forwarding globally on the router, typically with the IPv6 unicast routing command. This allows the router to actually process and forward IPv6 packets. Then, you enable OSPFv3 on a specific interface. You can do this either by configuring an IPv6 address directly on that interface, or sometimes by explicitly enabling IPv6 processing on it and then associating that interface with an OSPFv3 process ID, and crucially, an area.
Right, the area. So OSPFv3 builds this incredible detailed map. But what happens when your network, or maybe your neighborhood, as you put it, grows to the size of a city, or even a country? How do you stop that map from becoming overwhelming? How do you prevent information overload and keep that network GPS efficient across a huge enterprise or service provider network?
That's exactly where OSPFv3 areas become crucial. They are primarily designed for scalability and also to manage the scope of that LSA flooding we talked about. Instead of every single device needing to know every tiny detail about every other device in a massive network, areas help contain that information. They segment the network into logical domains.
Logical domains.
The most critical of these is the backbone area, which is always designated as Area 0. Think of it as the central nervous system of the whole OSPF domain. All other non-backbone areas must connect directly to Area 0, either physically or, as we might discuss later, logically. And the routers that sit on the border connecting Area 0 to these other areas are called Area Border Routers, or ABRs.
ABRs connecting to Area 0. Makes sense.
And within this structure, we also have the concept of area range. This is incredibly powerful for route consolidation. An ABR can basically summarize a whole bunch of specific IP prefixes within an area and advertise just a single aggregated address to other areas. This significantly reduces the size of routing tables in those other areas, making them much more efficient.
Summarization is key for scaling then.
Definitely. And then we have different area types. Each type has specific rules about which LSAs they allow in or out, kind of balancing the amount of information flow with network efficiency. A normal area is your standard area. All LSAs type 1, 2, 3, 4, 5 are flooded within it, providing full topology detail. A stub area is more restrictive. It specifically blocks Type 4 and Type 5 LSAs. Now, Type 5 LSAs carry routes learned from outside the OSPF domain entirely, maybe from BGP, for example.
External route.
Exactly. And Type 4 LSAs are needed to find the router, the ASBR, that's injecting those external routes. So blocking Type 4 and 5 drastically cuts down the database size within the stub area. It simplifies its routing table and reduces the processing load. Devices in a stub area just use a default summary LSA generated by the ABR to reach all those external destinations.
Okay, so stub areas simplify things by blocking external route details. What about the other types?
Well, a totally stubby area, TSA, goes even further. It blocks Type 3 LSAs in addition to Type 4 and 5. Type 3 LSAs are the summary routes for destinations within the OSPF domain but outside the local area. So a TSA only receives a single default summary LSA from its ABR for all routes outside its own area, whether they're internal OSPF routes or external routes. It's the most restrictive type.
Super simple, just a default route out.
Pretty much. Highly effective for, say, very small remote sites that just need a path out without needing details about the rest of the network. And finally, there's the not-so-stubby area, NSSA. This one's a clever variation of a stub area. It generally behaves like a stub area, blocking Type 4 and 5 LSAs coming in, but it allows for the limited advertisement of external routes originating within the NSX itself. It does this using a special LSA type, Type 7. These Type 7 LSAs can then be translated back into Type 5 LSAs by the NSSA ABR to be propagated into the rest of the OSPF domain.
Ah, so it's stubby but can introduce some external routes if needed.
Exactly. It's useful when you need to connect to another routing protocol, maybe a small BGP peering, within what should otherwise be a stubby environment, without making it a full normal area and flooding all external LSAs everywhere.
It's a fantastic breakdown. It really sounds like each area type offers a specific trade-off: control versus information density versus management overhead. So for an administrator designing a large network, how do you decide which area type is most appropriate? And what are some common pitfalls, maybe, of misapplying one?
It really boils down to the purpose and scale of that network segment. You typically use a totally stubby area, like I said, for a small remote branch needing minimal routing info. A standard stub area might be for a larger regional office still wants to limit external write flooding, but needs to know about specific internal OSPF subnets in other areas. NSSAs are niche but perfect for integrating some external routing within a stubby design. The biggest pitfall: violating that core OSPF backbone rule, never having an area that isn't somehow connected physically or logically to Area 0. That breaks the hierarchy. Another common issue is improper summarization, either summarizing too aggressively, which can hide necessary path details, or not summarizing enough, which kind of defeats the purpose of reducing routing table size.
Fascinating. Design choices with real consequences. Now, you mentioned logical connections to Area 0. What if you have an OSPF-v3 area that, for whatever reason, can't directly connect to the backbone, Area 0? Maybe it's a legacy design, an acquisition, maybe a physical link broke. Is it just cut off, or is there a clever way to maintain that essential connection?
This is precisely where virtual links come into play. And they are, well, a crucial concept, albeit sometimes complex, for maintaining OSPF's strict hierarchical structure. Imagine, like you said, Area 0 gets physically partitioned, or maybe you have an area, Area 5, let's say, that only connects to Area 1, and Area 1 connects to Area 0. Area 5 has no direct path to the backbone. Instead of redesigning the whole network or pulling new cables, a virtual link lets you create a logical, tunnel-like connection between that non-backbone area's ABR, the one in Area 1, and the backbone Area 0 through the transit area, Area 1 in this case.
So you tunnel through another area to reach the backbone.
Essentially, yes. It's configured between two ABRs across a non-backbone transit area. It tricks OSPF into thinking there's a direct link to the backbone for the purposes of the SPF calculation and maintaining that Area 0 connectivity rule. It ensures all areas can logically reach Area 0, preventing what we call a discontiguous backbone, which OSPF generally doesn't allow.
Clever workaround. Okay, so OSPF-v3 has these intelligent mechanisms for managing its own internal world with areas and virtual links.
Yeah.
But networks rarely operate in a vacuum, right? Most big environments mix OSPF with other protocols like BGP, maybe some static routes. How does OSPF-v3 handle routes coming from those outside domains? And how does it simplify its own complex internal information for efficiency?
Yeah, that interoperability and efficiency piece is critical. OSPFv3 offers several key mechanisms here. First is route redistribution. This is the process that allows OSPFv3 to import routes learned from other routing protocols, BGP, RIPing, EIG or PD6, static routes, you name it, into its own OSPFv3 domain. This is absolutely essential for letting different parts of a larger network, maybe running different protocols for historical or technical reasons, communicate seamlessly.
So it learns routes from its neighbors even if they speak a different language.
Exactly. Then we have default route origination, an autonomous system boundary router, an ASBR that's a router running OSPF-v3, and another protocol like BGP can advertise a default route into the OSPF-v3 domain. This is vital because it provides a path for all unknown destinations. It essentially gives routers inside the OSPF domain a way out to the internet or perhaps to a core network segment without needing a specific route for every single destination out there.
The path of last resort.
Precisely. And for further efficiency, especially with those external routes coming in, an ASBR can perform external route summarization, similar to area range summarization, but this applies to the external routes being redistributed into OSPF-v3. The ASBR can consolidate potentially thousands of external routes into a smaller set of summary addresses. This dramatically reduces the number of Type 5 LSAs floating around and shrinks the writing tables inside the OSPF-v3 domain, which boosts performance and reduces router load.
Makes sense. Control the flood of external information.
Absolutely. And finally, for really granular policy control, OSPFv3 supports filtering OSPFv3 routes. Network administrators can use tools like prefix lists or more complex route maps to precisely control which specific routes get advertised or accepted between areas or when redistributing into or out of OSPFv3. This gives them fine-grained command over the information flow, ensuring only necessary and authorized routes are propagated, which is often important for security and policy compliance.
It really sounds like OSPF OSPFv3 is incredibly versatile. It's not just about navigating its own world, but also interacting smartly, concisely with the larger network universe, streamlining its maps and providing flexible policy tools. Okay, now shifting gears slightly, given how dynamic and, frankly, critical modern networks are, how does OSPFv3 make sure it can adapt quickly when things change, like a link goes down or comes back up? How does it stay resilient without just getting stuck or taking ages to recover?
Resilience is definitely baked into OSPFv3 through several timer mechanisms. These timers are all about balancing responsiveness with system stability. You don't want the network thrashing itself unnecessarily. The SPF timers, specifically the SPEF delay and SPIS hold time, are crucial here. These control how quickly and how often OSPF recalculates the shortest path first algorithm after a topology change is detected. It's a careful calibration. If you set the delay too low, the router might recalculate SPF too many times if a link is flapping rapidly, which burns CPU cycles.
Right, you don't want it overreacting.
Exactly. But if you set the hold time too high, the network might be slow to converge after a genuine failure. So these timers introduce a delay before the first calculation and then a hold down period between subsequent calculations during times of instability. We also have LSA refresh timers. All OSPFv3 LSAs have maximum age, and they need to be refreshed periodically, typically every 30 minutes, even if nothing has changed. This ensures the database stays current and detects routers that might have silently disappeared.
Like a heartbeat check.
Kind of, yeah. And complementing this is the LSA pacing interval. Instead of potentially flooding thousands of refreshed LSAs all at once every 30 minutes, which could spike CPU usage, this timer allows the router to pace the sending of these refresh LSAs over a configurable interval, smoothing out the load.
So it's a carefully orchestrated dance of timers then. Not too quick to thrash, but fast enough to react to real failures. Finding that sweet spot must be a constant focus for network engineers. What about planned maintenance? Like when devices need a reboot for an upgrade, those are critical moments. How does OSPF v3 minimize disruption then?
Right, planned downtime or even unplanned restarts need handling. OSPFv3 incorporates graceful restart, GR, sometimes called nonstop forwarding, NSF helper mode. This is a really neat mechanism. It allows an OSPFv3 router to restart its OSPFv3 process, maybe after a software upgrade or even a minor crash, without disrupting the actual forwarding of traffic through it, at least for a short period.
How does it manage that?
Well, the restarting router signals its neighbors that it's doing a graceful restart. Those neighbors then agree to keep forwarding traffic based on the last known good routing information they had from the restarting router, essentially pretending it's still fully active for forwarding purposes. Meanwhile, the restarting router quickly reestablishes its OSPF adjacencies and rebuilds its routing table. Once it's done, normal OSPF operation resumes. It significantly minimizes service interruption during these events.
That's clever. Keeps the traffic flowing.
Yeah. And building on that, there's nonstop routing, NSR. This is usually a more advanced feature, often found on higher-end routers with redundant control planes. NSR aims to maintain routing protocol state across a control plane failure or switchover. So if the main routing engine crashes, a standby engine can take over almost instantly, already having the synchronized OSPF state, ensuring continuous forwarding without even the brief interruption that GR might involve. It's designed for really high availability.
Wow, okay. That's some serious engineering for uptime. And of course, in today's world, security is absolutely paramount. How does OSPFv3 protect itself? How does it stop malicious actors from injecting bad routing information or tampering with updates? It feels like an open protocol could be a major target.
You're absolutely right. Routing protocols are prime targets, and securing OSPF v3 is a critical concern. OSPF v3 authentication is the mechanism for this. Its main goal is to ensure that OSPF v3 routers only accept routing updates from trusted authorized neighbors, preventing unauthorized devices from injecting false routes that could black hole traffic or create loops. Unlike OSPF v2, which had options like clear text or MD5 authentication built directly into the OSPF header, OSPF v3 takes a different approach. It primarily relies on the IP layer's security mechanisms, specifically IPsec.
IPsec, so it leverages the standard IP security framework.
Exactly. This is actually a significant architectural decision. It integrates routing security more deeply into the overall network security posture rather than having protocol-specific methods. OSPF v3 typically uses IPsec's authentication header, AH, or, more commonly, encapsulating security payload, ESP, in transport mode. ESP can provide both authentication, ensuring the packet came from the stated neighbor and hasn't been tampered with, and optionally, encryption of the OSPF payload itself. For the authentication part, it uses strong hashing algorithms like HMAC SHA-1 or the much preferred HMAC SHA-256.
SHA-256 is much better these days, right?
Definitely the recommended standard now. So ITsec ESP essentially wraps the OSPFv3 packet, adding authentication data and potentially encrypting the OSPF message content before it's sent over the wire. The receiving OSPF router uses a pre-shared key or digital certificates managed via a security association SA to verify the authenticity and decrypt if necessary. And to manage the keys themselves, which need to be changed periodically for good security hygiene, OSPFv3 can work with IPsec's key management mechanism, sometimes involving a key rollover timer. This helps manage key activation times to allow for seamless, non-disruptive key changes, which is vital for maintaining security without causing network outages.
That level of sophisticated integrated security using IPsec, plus the resilience features like graceful restart, it's truly impressive. It ensures that the network's GPS, as you called it, is not only accurate and adaptive, but also rigorously protected. It really speaks volumes about how critical these underlying protocols are. So we've navigated through quite a bit of the fascinating world of OSPFv3 today, from its fundamental principles as an IPv6 link state protocol to its advanced features like how it uses areas, virtual links, manages external routes, and all underpinned by those critical security and resilience mechanisms.
Yeah, and if we just connect this back to the bigger picture for a second, OSPFv3 really represents this continuous evolution in network routing. It's a testament, I think, to how network design constantly adapts to demands for larger address spaces with IPv6, greater scale, and definitely more stringent security. Understanding these protocols isn't just about memorizing commands, is it? It's about grasping the stability, the efficiency, and the underlying security architecture that really underpins our entire digital communication landscape. It's kind of the silent, tireless engine behind our connected world.
Well said. And for you, our listener, the next time you connect to the internet or access a cloud service, maybe take a moment to consider the hidden complexity and the ingenious design of protocols like OSPFv3, tirelessly working behind the scenes, making sure your data finds its way quickly, efficiently, and, as we've heard, securely. And as always, we like to leave you with a provocative thought. Here's one for today. As routing protocols like OSPFc3 become increasingly automated, more intelligent, maybe even self-healing with AI and machine learning down the line, how might the role of the human network engineer evolve? Will their focus shift away from manual configuration and step-by-step troubleshooting towards more high-level architectural design, defining security policies, maybe understanding the AI that's optimizing things in real time? What new skills will be paramount in maintaining and evolving this ever-expanding, ever more complex digital future? Something to think about.